Hello everyone, this is 11th lecture, and in this lecture we shall discuss about the electric field intensity due to a dipole. There are two cases in it. The first is on axial line. First of all, we consider a dipole, and we know that a dipole contains two equal and opposite charges plus q and minus q. And midpoint of dipole is O, and distance of each charge from midpoint is A, and separation of charges is 2A. Axial line is the axis that passes through both the charges of the dipole, and we consider this is the axial line, and we consider a point P on this axial line which is at a distance r from the dipole. First of all, we consider a dipole plus q and minus q. There are two charges are there, and O is a midpoint. A and A are the separation of charges, and then we shall calculate the electric field intensity. Consider a dipole of charge plus minus q, midpoint O, and the separation of charges is 2A. P is a point on axial line at distance r from O. Now we shall consider the electric field intensity at point P due to this positive charge and due to this negative charge. So electric field intensity at P due to plus Q charge EA, and it will be KQ upon R plus A whole square away from the direction of the electric field. This is plus Q charge, this is point P. Had we consider a positive charge, and this charge is repelled by this charge, so according to the formula KQ upon R square, KQ is there, and the distance from this charge to this point is the distance R plus A, and the direction will be opposite to the dipole. Electric field intensity at P due to minus Q charge, and EB is equal to KQ upon R minus A. This is the total distance R, and this is A. It is subtracted, so this distance will be R minus A, and the direction will be towards the dipole. This direction is EA, and this direction is EB. We consider this is a point A and this is point B. Then net electric field, because both electric fields are opposite to one another. So net electric field E is equal to EB minus EA, because this value is greater, this value is smaller, so we subtract this value from this value, and E is equal to KQ upon R plus A whole square, R minus A whole square minus KQ upon R plus A whole square. KQ can be taken out. LCM will be R square minus A square whole square. Here is R plus A whole square minus R minus A whole square. Because it is divided by this and this value can be multiplied with this, take common, so R plus A square minus, in this case, when R square minus A square whole square is divided by R plus A square, then we get R minus A whole square, and when it is multiplied with KQ, KQ is taken common, so R minus A whole square. We know that this is the formula of A plus B whole square minus A minus B whole square, and we know that A plus B whole square minus A minus B whole square is equal to 4AB. According to this formula, E will be is equal to KQ into 4RA upon R square minus A square whole square. 2A, Q into 2A, we arrange these values into R upon R square minus A square whole square. Q into 2A, we know that P. So 2K P R upon R square minus A square whole square. If R is very much greater than A, then A square can be neglected. When A square is neglected, then we obtain R power 4. One power is just cancelled out. So the electric field intensity due to dipole at the on axial line is 2 kp upon R. And in vector notation, E is equal to 2 kp upon R cube into R. Now the second application is electric field intensity due to a dipole on equatorial line. What is equatorial line? We consider again a dipole. Here is plus Q, this is minus Q, this is the midpoint, and the separation of each charge from midpoint is A, and separation of charges is 2A. And the equatorial line is the perpendicular line passing through the midpoint and perpendicular to the dipole. And we consider a point P at distance R from O, and then we join the point A and B from P. This distance we consider X. Now, due to this charge, electric field intensity will be along this direction, EA, and due to this negative charge, the electric field intensity will be along this side, EB, because this is negative charge, and negative charge attracts the considered positive charge, and this positive charge repels this considered positive charge, so the direction of electric field intensity will be along the direction of repulsion, that is EA, and here is the electric field intensity has direction along the direction of attraction, that means along towards minus the charge. Consider dipole of charge plus minus q and separation of charges 2a with the midpoint P is a point, a distance R from O on equatorial line. This point is P. Now we draw a parallel to dipole line. If this angle is theta, then this angle will also be theta. And if this angle is theta, then this angle will also be theta. These are the corresponding angles and these are the alternate angles. Now we resolve the components of electric field intensity EA into components. Here will be the cos component EA cos theta. Here it will be EA sin theta. Now EB is to be resolved, EB cos theta, and here it will be EB sin theta. The value of EA is equal to EB because the magnitude of both charges is Q and the distance x from both charges. So the distance x square. So EA is equal to EB is equal to KQ upon x square. This relation is obtained. We consider it equation number first. Now when we resolve the components, EA cos theta and EB cos theta are along same direction, so they add up, and EA sin theta and EB sin theta are equal in magnitude, opposite in direction, so they cancel out. So the sine components means vertical components are cancelled out and cos components means horizontal components are add up. EA and EB are resolved into components horizontal components EA cos theta and EB cos theta are along same direction, so add up, and EA sin vertical components EA sin theta and EB sin theta are equal in magnitude because EA and EB are equal and thetas are equal in magnitude and opposite in direction. So they cancel. So net electric field will be EA cos theta plus EB cos theta, and we know that EA and EB are equal, so we can write here 2EA cos theta And now we can put the value of EA or EB to KQ upon x square cos theta. Now we consider triangle POA. POA. This angle is theta, and this is hypotenuse, this is base, this is perpendicular. So according to Pythagoras theorem, x square is equal to r square plus a square. And cos theta is equal to base upon hypotenuse, means a upon x, and the value of x according to this is r square plus a square power half. When we put all values, E is equal to 2kq upon r square plus a square into a upon r square plus a square power half. So net electric field E is equal to kq into 2a. This 2 is taken with a. Now r square plus a square power 3 by 2. Q into 2a is the electric dipole moment, so Kp upon r square plus a square power 3 by 2. If r is very much greater than a, then a square can be neglected. So E is equal to Kp upon R. And we derived for XL line 2 Kp upon R2. So E equatorial ratio E axial means Kp upon R2 is equal to 2 Kp upon R2, means 1 ratio